All right, so let's say you're in the mood to make some chocolate chip cookies. You find a chocolate chip cookie recipe and it lists all the ingredients that you're going to need to make your cookies. It tells you how much of each ingredient, and then it tells you how many cookies you should end up making if you follow this recipe. So this chocolate chip cookie recipe tells me in what ratio to mix my ingredients together, and then it tells me how much product, how many cookies I should end up with. In chemistry, we have the same exact thing. Instead of actual recipes like a chocolate chip cookie recipe where we have cups and teaspoons and how many eggs you're going to need and how many dozens of cookies you're going to end up making. In chemistry, our recipes are balanced chemical equations. And we approach this new topic called stoichiometry. So go ahead and take a moment here and write down what stoichiometry is. And stoichiometry is simply using the balanced chemical equation as a recipe for making products. Instead of using cups and teaspoons and tablespoons, we're going to be using moles instead. That balance equation, the units are always going to be in moles. Just like our chocolate chip cookie recipe uses different units, cups, and teaspoons, our balance equations are a little bit more simple. They're just always going to use moles. And it tells you in what ratio to mix our reactants together. And what we're going to use are those coefficients as our mole ratios. Those coefficients are going to tell me, okay, how much of each reactant are we going to need? And then if I combine them in that proportion, how much product can I expect to make? So it's much like our chocolate chip cookie recipe. If I mix these ingredients together in this amount, I should make this many cookies. Same thing here with balanced chemical equations and chemical reactions. If I mix our reactants together according to our balanced chemical equation, I should be able to predict how much product we're going to end up making. And this is the really, really powerful part about stoichiometry. All right, so let's just dive into an example. Example number 1 here, we have the balanced chemical equation of sodium and chlorine reacting to make sodium chloride, table salt. And so again, our balanced equation is a recipe for making products. And the units that we use are moles. And those moles are represented in the coefficients from our balance equation. Okay, so I'm going to read this in terms of our recipe. We're going to say 2 moles of sodium react with 1 mole of chlorine to make 2 moles of sodium chloride. And they're always going to react in this proportion, in these ratios, according to our balance equation. So if I mix together 2 moles of sodium plus 1 mole of chlorine, we will make exactly 2 moles of sodium chloride salt. So we can write this out and say, for every 2 moles of sodium that react, and I'm getting that 2 moles of sodium from its coefficient from the balance equation, 2 moles of sodium here. For every 2 moles of sodium that reacts, 1 mole of chlorine is going to be required to react with it. And I'm pulling the coefficient for chlorine. And since I don't see a number in front of the chlorine, we can assume its coefficient is 1. And we know that 2 moles of sodium chloride are produced. And again, I'm pulling the coefficient for the sodium chloride. So here's our recipe. For every 2 moles of sodium, we're going to need 1 mole of chlorine, and we combine them together, and we're going to make 2 moles of sodium chloride. Now, what happens sometimes when we cook and we bake? Sometimes we want to double the recipe because we want to make more. So I can do the same thing with our balance equation. Let's say I want 4 moles of sodium chloride produced. So if I want to double the amount of sodium chloride, then I'm going to need to double the amount of reactants as well. So we're going to need 4 moles of sodium and 2 moles of chlorine to make 4 moles of sodium chloride. But again, the ratios between these 3 chemical species is remaining the same. The ratio is 2 sodiums to every 1 chlorine to every 2 sodium chlorides. Now I can take these words on my recipe and write them as unit conversions or conversion factors, as you've heard us say. All right, so I'm just taking those words and turning them into conversion factors that we're used to. What we're really saying with this recipe is 2 moles of sodium equals 1 mole of chlorine, which also equals 2 moles of sodium chloride. And again, those number of moles are the coefficients from the balance equation. Now remember, we can take conversion factors and rewrite them in like a fraction form when we start to do dimensional analysis. We can take one part of our conversion factor and put it over another part of our conversion factor. So I could say 2 moles of sodium over 1 mole of chlorine. What we're saying is, when we write them as fractions, is that the numerator is equal to the denominator, which is exactly what we've said here in our conversion factor. 2 moles of sodium is equal to 1 mole of chlorine. I could flip it around and I could put chlorine on top and the sodium on the bottom. We're saying the same thing here. 1 mole of chlorine is equal to 2 moles of sodium. But keep in mind, the number of moles for every single chemical species here matches its coefficient from the balance equation. Now, sodium and chlorine is not the only fraction I could write. I could write sodium and the sodium chloride in the same fraction. So here I have sodium and sodium chloride in the same fraction. According to our unit conversions, our conversion factors, it is the same thing. It's saying 2 moles of sodium, and then we'll just jump over here to 2 moles of sodium chloride. So they are equal to one another, and that's why I'm writing the fractions such as this. Our 2 moles of sodium over 2 moles of sodium chloride, or flip it around and put 2 moles of sodium chloride over the 2 moles of sodium. Now there's one more type of fraction we could write, and that's involving the chlorine and the sodium chloride. So we're going to put the coefficient of 1 mole of chlorine over the coefficient for the sodium chloride, 2 moles of sodium chloride, or flip it around and get our other fraction possibility. Now, so you see all the combinations of fractions that we could have for this balance equation. Once we get really good at this, we're not going to have to write out all the possible fractions, but we're doing this here for our first example so you see how the coefficients are used as unit conversions and how we can take those conversion factors and rewrite them in these fraction forms, and we can then use it in dimensional analysis. All right, so here in example 2, I'm asking how many moles of sodium chloride are produced when 5 moles of chlorine react. And I've rewritten the balance equation from above. So when we get these problems, we always want to identify what is our starting value and what is our ending value. What are we trying to solve for? So our start value is going to be this given value of 5 moles of chlorine. So I'm going to label that as start. And what are we trying to convert those moles of chlorine into? We're trying to convert them into moles of sodium chloride, and that's going to be our end value. And so we're trying to convert between moles of chlorine and moles of sodium chloride. And one method comes to mind that we've used before that allows us to convert between any two units as long as we have a conversion factor. And that method is called dimensional analysis. So we're going to take our start and we're going to write its value, 5 moles of Cl2. Remember, you can put that over 1 as a placeholder, and you're going to multiply it by a conversion factor, but in fraction form. And remember, we've already written down our possible conversion factors for this given reaction. Okay, so we're going to go back and look at our fractions and pick one that is suitable here. And keep in mind, the goal of dimensional analysis is to cancel out the starting unit. And so I'm looking for a fraction that's going to allow me to cancel out moles of chlorine. All right, so here are my fractions. I'm looking for one that has moles of chlorine in the denominator because I know I need to cancel it out. So I have a few options. I can select this one here, possibly, or another one that has chlorine on the bottom is going to be this one down here. Now, only one of these is suitable for our problem. Since our end goal is to convert to moles of sodium chloride, we're going to want to pick the fraction that has the moles of sodium chloride at the top. So this one down here, bottom right, is the one we like to select. All right, so we insert the appropriate fraction conversion factor, and we see here that the moles of chlorine are going to cancel because I got one on top, one on the bottom, and the end unit is moles of sodium chloride. I got my end unit there in the numerator, so I know I'm ready to do the calculation. I pick up my calculator. Oh, actually, no, don't pick up your calculator. You can do this in your head. 5 times 2 is the math that you were doing. Remember, you multiply all the tops together, and then on the bottom, it's just going to be 1 times 1, which is just 1. So here the answer is 10. And we copy down our unit. That is going to be moles of sodium chloride, and that is our answer. We're going to end up producing 10 moles of sodium chloride from 5 moles of chlorine. And let's just look at our balanced equation. Does that make sense? We said in our balanced equation the coefficient of chlorine is 1. For every 1 chlorine that reacts, we always make 2 moles of sodium chloride. So if I increase the amount of chlorine up to 5 moles of chlorine, it does make sense that we are going to get 5 times 2 moles of sodium chloride. So we're just essentially multiplying everything here by 5. And we know that sodium chloride is always going to have to be double the amount of chlorine because the coefficient of sodium chloride is twice the coefficient of the chlorine. So here you have it. Here is your dimensional analysis work for your very first stoichiometry problem. All right, let's try a third example. How many moles of NH3, also called ammonia, are produced when 2.5 moles of nitrogen react? Okay, so again, we're going to identify our start. We're going to identify our end. So our start is the given number, 2.5 moles of nitrogen. Our end is moles of ammonia. They're asking me to convert moles of nitrogen into moles of ammonia. So our work, always got to take our start value and write it down, 2.5 moles of N2 over 1 times a fraction. Okay, and I haven't written out the fractions yet, but let's take a look at this. We can do this without having to write all the fractions out. I know the power of dimensional analysis. I know moles of nitrogen has to go on the bottom here because I want that unit to cancel. And remember the number we put in front of moles. It's going to be the coefficient. And so I go back and look at my balance equation. There is no coefficient written in front of nitrogen, so I assume it to be a number 1. And so that 1 gets carried down here, 1 mole of nitrogen. And since my end goal is to have an answer in terms of NH3, the product, I'm going to take the coefficient of that product and put it in front of moles of NH3. So right here, what I'm highlighting, guys, those are your coefficients from the balance equation. When I have coefficient over coefficient, we call this a mole ratio. When you have moles over moles, we are comparing the moles of ammonia to the moles of nitrogen. That is the essence of what stoichiometry is. It's using mole ratios to convert between moles of one chemical and moles of a different chemical that happen to be in the same chemical reaction. So I know moles of nitrogen are going to cancel. You are left with this unit of moles of NH3. Go back and check your question. Hey, yes, that is my end goal. I said, hey, I want NH3 moles as my answer. And so that's how I know I'm done with the setup. And now it's time for the math. It is 2.5 times 2 all over 1 times 1. And 2.5 times 2 is 5. And I copy down that unit of moles of NH3. And so here I have just used the power of that balanced chemical equation recipe. For every 1 mole of nitrogen that reacts, we're going to produce 2 moles of ammonia. So if I change the starting value to 2.5 moles of ammonia, I know we're going to make double the amount of ammonia. And so 2.5 times 2 is at 5 moles of ammonia produced. All right, here, example number 4, if 0.8 moles of NH3 ammonia are produced, then how many moles of hydrogen reacted? So this is like me saying, hey, we made 2 dozen cookies. How many cups of flour did we have to use? This is the same thing here. I'm telling you, we made this much product. Please tell me how much reactant we used to make that much product. But the process is still the same, guys. We're going to identify the start, which is always a given number. It's 0.8 moles of NH3 for this problem. Identify the end. What are we trying to solve for? We're trying to solve for moles of hydrogen. So take your start, please, and rewrite it here in our dimensional analysis. You can put it over 1. And then we're going to multiply it by a conversion factor. I know moles of NH3 has to go on the bottom, and we're trying to solve for moles of hydrogen, so that's going to go on top. And then, hey, I got moles over moles, moles over moles. That is what we call a mole ratio. Where do I get the numbers for a mole ratio? That's right, the coefficient. So I go to my balance equation, I look for the coefficient of the hydrogen. It is 3. So we're going to write 3 moles of hydrogen. And then I repeat for the ammonia. I go to the balance equation, its coefficient is 2. So I'm going to write 2 in front of the moles of ammonia. And there we go. We've just used our coefficients in a conversion factor inside a dimensional analysis. And I have to put moles of ammonia on the bottom because I want those units to cancel. And I want to end here with moles of hydrogen. And so I know that I have my end right here in the numerator, so I know to pick up the calculator and do this math. So this math, remember, is going to be multiply the top, then you multiply everything that's on the bottom, and then you divide. And so we're going to get an answer here of 1.2 moles of hydrogen. Okay, so if we make 0.8 moles of ammonia, I can then figure out how many moles of hydrogen we used to make that amount of ammonia. Alright, so what is our take-home message from this lesson? What should you have learned from watching and taking notes on this video? We should know that balanced equations are chemical recipes. They tell me how much reactants to mix together, and it's going to tell me how much product we're going to make. The coefficients in a balanced equation represent moles, and mole ratios are used as conversion factors to convert from moles of one chemical to moles of another chemical. And this whole process of using mole ratios is known as stoichiometry.